Alright, this video is an introduction to chemical equilibrium in the grade 12 regular and AP chemistry classes. So if you missed this in class, this will help review what we did. So we're looking at, first of all, just an introduction. For those of you who've seen equilibrium before, grade 11 chemistry, you may remember that we talked there about physical equilibria. This unit deals with chemical equilibrium. So in chemical equilibrium, we first of all recognize that most chemical reactions are reversible, just like most physical processes are also reversible. What does that mean? Well, a simple example of that would be the physical equilibrium that we see here in the middle of the page. Water can come in a solid state, and ice, and we can melt it to make liquid water. Of course, you could also take liquid water and you can freeze it. So this reaction can go in the forward direction, or it can go in the reverse direction. So freezing, melting is a reversible process. Less obvious is that chemical processes are also reversible. In grade 9 science, you might remember doing an experiment on electrolysis of water, where we took liquid water and we ran electricity through it, and we collected hydrogen gas and oxygen gas. So we were decomposing water into its elements. But we also did many times in the lab little explosions with hydrogen gas, where we confirmed the presence of hydrogen gas by putting a burning wooden splint into a test tube of the gas, and we heard a popping sound, an explosion. What you were really doing there was taking hydrogen and burning it with oxygen, so you were doing the reverse process and converting it back to water vapor. So there's a good example of a chemical reaction which is also reversible. So most chemical reactions, or many of them, are reversible, and that's what this unit's going to be about, those reversible reactions. In this little animation, we're going to follow a reversible reaction, a relatively simple one. We have hydrogen gas, H2, and iodine vapor. So this is happening at a high temperature, 425 degrees Celsius. At room temperature, iodine is a solid, but at the high temperature, it's a gas. And they will react and form HI, okay, HI, hydrogen iodide. And we see a ratio there, 1 to 1 to 2. On the left, we see a graph which should look familiar. It's a graph of concentration versus time. And we saw that in our kinetics unit, concentration time graphs. On the right, though, we see another graph which is a little bit different. It's a graph of rate of reaction versus time. And that's one that we didn't look at very often in the kinetics unit. In the left-hand graph, we see that in this experiment, the hydrogen is starting off at some initial concentration, the iodine less, and the HI starts off at nothing. There's no HI in the container initially. And so let's start the reaction and just see what happens as it proceeds. So we're, clicking on the arrow button, start the reaction, and I'm going to have to do that on my computer. There we go. So the reaction proceeded here, and at this point in the process, we can look and see that the hydrogen concentration is dropping. The iodine concentration is dropping the same rate because their ratios in the balanced equation are 1 to 1. And the HI is increasing, it's the product, and so it's increasing from 0 up to some higher concentration, and it looks to be increasing twice as fast as the others are decreasing. And again, that's from our kinetics unit, not surprising. There's 2 HIs being produced for every 1 hydrogen and for every 1 iodine. Now, when we looked at these numbers in class, we realized that there's a little bit of an error, I think, in this animation, but we'll see if we can see that here again. So now let's proceed a little bit further in the reaction. So going a little bit further, we've reached a point now where the concentrations are starting to level off. Now these numbers here appear to be, I think, yeah, this number here is not supposed to be a 3. Okay, this number here, we saw this in class and realized there's a mistake there in the whoever made this animation. Its actual value is supposed to be 5. And let's just see if that makes some sense here, even now. And we can look at the initial hydrogen concentration. It started at 12 molarity, and the iodine started at 6 molarity. Well, they react in a 1-to-1 ratio. So if we look at the final iodine concentration, it seems to be at about 1.5. I can agree with that looking at the graph. So if it began at 6 and fell to 1.5, then the iodine has dropped by how much? 6 take away 1.5 means it dropped by 4.5 molarity. While the hydrogen started at 12 molarity. And so during that same period of time, it should have dropped by the same amount because its ratio is 1-to-1. So if it started at 12 molarity, it should have dropped from 12 down to, let's see, 8, and then down to 7.5. So really the hydrogen in this animation should have done something like that, not what you see in yellow. So that's actually a bit of a mistake in the animation. But the basic point is that the concentrations have leveled off at this point. The HI concentration, if it started at 0, and these two were losing 4.5, should have actually increased to twice that because of the 2-to-1 ratio. It should have increased to 9. So really it should have gone something like that, rather than what you see in the picture. But nonetheless, if I erase my drawings there and just look at the original animation, we can see here the point that it's trying to get across, even though it's slightly flawed, is that the concentrations have leveled off. If we look at the rate graph on the side, it's been forming at the same time. Notice that the rate of the forward reaction started here at this high number, while the reverse reaction rate started at 0. Can you explain why that would be? Why is the reverse starting at 0 in this experiment? The answer, of course, is that the HI, which is the reactant in the reverse reaction, starts at 0 concentration. So therefore, the HI being missing, it's 0 concentration, there could be no reverse reaction initially. So the reverse rate starts at 0. But as the reaction proceeds and you get more and more HI, from our unit on kinetics, we know that as its concentration goes up, the reverse rate will go up as well. So this graph increases like that. The forward rate is decreasing, again easily explained from our kinetics unit, because the H2 and the I2 concentrations are dropping. So as their concentrations drop, we know that concentration of reactants is a factor that affects rates. That'll cause the forward rate to drop. So the forward rate is dropping over time. But notice that at this time where the concentrations start to level off, look what's happening to the rates of the forward and reverse reaction. That's really, really important. I'm going to step forward in the animation one more time so you can see what the next phase is. If we let the reaction continue, not shockingly, the concentrations remain where they were and the rates remain what they were. So what we have here at this point marked by the green dotted line on both graphs is the point of chemical equilibrium. The definition of equilibrium is very important, so make sure you've got that. The equilibrium is the point in the reaction where the forward and the reverse reaction rates become equal. So when the rate of the forward reaction is equal to the rate of the reverse reaction, you have chemical equilibrium. If you were watching the reaction, you would claim, looking at it, that it looks like the reaction has stopped because the concentrations of all the reactants and of the products have stopped changing, right? Their concentrations are no longer changing, so it would appear that the color of the system, the pressure of the system, the temperature of the system would all stay constant once you've reached equilibrium. However, keep in mind that both the forward and reverse reactions are always happening. They're simply happening at the same rate. So although it appears to have stopped, nothing really stops inside that container. Collisions are always happening. Both reactions are always happening. So we sometimes refer to equilibrium as being a dynamic equilibrium. That's kind of ironic if you think about it, because the equilibrium word implies static. It implies nothing's really changing. the rates are balanced, and yet the word dynamic is thrown in front to emphasize that if you looked at the molecular level, you'd be seeing reactions happening all the time. Although it looks like it stopped, it never actually does stop reacting. All right, in this animation, we're going to see something kind of similar. This time we see a particulate representation here in the box on the left. We see these little purple particles. These are supposed to represent cyclopropane particles. A little organic chemistry there. Propane, you remember, has 3 carbons, and cyclopropane, those 3 carbons are joined in a ring like this. The ring is highly unstable, so the ring tends to break apart, and when it does, you form this propene molecule, which again has 3 carbons but joined with a double bond in there between 2 of them. Organic chemistry is not hugely important in AP chemistry, but you can see what's happening. So there's this equilibrium between the two. The person who's doing this experiment has started with 1 molarity cyclopropane. So the purple dots here represent the cyclopropane particles. The graph below it, the bar graph, shows an initial concentration of 1 molarity, and that's the cyclopropane, and below it, 0 molarity, that's the product, the propene. On the graph beside it, the line graph, we're going to see the purple line representing the change in cyclopropane, and a red line for the change in propene. Since the cyclopropane is starting at 1 molarity, we expect it to start up here in purple, and then it's the reactant, so it's going to drop over time. So let's initiate the equilibrium and see what happens as we do. So you can see there in the box, the particles, we've suddenly got a lot of red particles. And looking at the bar graph below, the concentrations now that we've reached an equilibrium state have dropped dramatically in the cyclopropane to 0.15 molarity and have increased to 0.85 molarity. Now again, if you think about the ratio here, these are reacting in a 1-to-1 ratio. So for every 1 cyclopropane that disappears, you get 1 propene particle. So if the cyclopropane started at 1 molarity and ended here at equilibrium at 0.15 molarity, then it lost 0.85 molarity. That 0.85 was turned into the propene. So the red bar right there went from 0 up to 0.85. Those changes are equal because the ratio was 1-to-1 in the balanced equation. On the graph, we can see that reflected by the symmetry in the graph. The red curve started at 0 and went up to 0.85, and we can tell we're at equilibrium because, again, it's leveled off here. The concentration is no longer changing. And similarly, the purple curve dropped from 1 down to 0.15 and is leveled off here at the same point. Equilibrium has to be reached at the same time for everything in the container. Now the question here is, what would happen to this graph if we suddenly shoot in some extra reactants? So what if we were to add some cyclopropane to the system? Let's just get a syringe filled with cyclopropane and instantly squirt some extra cyclopropane into the container. What would that do to this graph? Well, the cyclopropane is the purple curve here, and we're going to suddenly squirt in some extra cyclopropane. So we expect that this purple graph is going to suddenly increase in concentration, something like that. And then, depending on how much we add, and then with extra cyclopropane, I hope you realize that the reaction is going to again proceed to lose some of the extra cyclopropane. So let's try it and see what happens. So let's squirt some extra in there. Boom, we've suddenly got an increase in the cyclopropane, and now let's reinitiate the equilibrium. Notice we've got 0.4 molarity instead of the 0.15. So let's reinitiate equilibrium. Predict what'll happen to the graph as we do. Right? Did you predict that the red curve would increase like it is here again? And did you predict the purple curve would decrease like it did? And if you compare those, you'll notice again, because the ratio is 1-to-1, that the amount that the red curve increases by from this starting point here, so from this starting point So this equilibrium point, if you look at how much that changed, it should be the same as the amount from this starting point to this ending point for the cyclopropane. So the new equilibrium has 1.06 molarity and 0.19 molarity. Notice if you look at the graph closely that the cyclopropane never achieved its original concentration before you added some. So here we were at 0.15 molarity. We squirted in some extra up to 0.4 molarity. It then dropped down to 0.19 molarity when it reached equilibrium. The new equilibrium still has more cyclopropane than it did before, and that's because we squirted some extra cyclopropane in. Now, if we were to calculate what's called an equilibrium constant, if you're looking at this as a review later, you could calculate Kc for the reaction before and after we squirted in the cyclopropane, the extra cyclopropane, and you should note that you get the same value, right? So you could try that if you're looking at this as a review. The equilibrium expression for a reaction like the one we just saw is based on the reaction as written, so this is a little bit easier than rate laws. Here we have a homogeneous, because everything is in the same phase, gases, a homogeneous gas phase equilibrium. So what we want to do is note that in this equilibrium, we have this equation, which we're going to call the equilibrium equation. Kc is the equilibrium constant, capital K, to distinguish it from our rate constants with little k's. The C there indicates that we're calculating it using concentrations, square brackets you see on the right. We can also calculate equilibrium constants using pressures in atmospheres, and so then we would call it a Kp instead. And the bullets on the right, you'll notice some things about this Kc expression. Notice that the products from the equation here become the numerator in the Kc expression, while the reactants become the denominator. So H2's concentration multiplied by I2's concentration is the numerator of Kc, and the Hi concentration is the denominator. Notice too that the coefficients in the balanced equation, so 2 for Hi and 1s for the H2 and the I2, they become the exponents in the Kc expression. So the H2 concentration is to the power of 1, so is the I2 concentration. The Hi concentration is squared because its coefficient was a 2. When there's more than one product or more than one reactant, notice that their concentrations are multiplied in the Kc expression. So H2 concentration multiplied by I2's concentration. A common little notational problem is that some students will take that 2 in the Hi in the balanced equation. For some reason, they write it down here in the brackets for concentration. Please do not do that. When you're writing the concentration, it's just the concentration of Hi, not the concentration of 2Hi. Okay, so do not make that mistake. So in this gas phase equilibrium, everything was included in the Kc expression. If there were aqueous species here, so Aq, we would also include them, because gases and aqueous species have concentrations which can change during the reaction. If you have a container of certain volume and you're producing more and more hydrogen gas, the concentration of hydrogen will go up. Similarly, if you've got something dissolved in a certain volume of solution and you produce more and more of a product in the solution, aqueous, then the concentration of that substance would go up. So aqueous and gaseous substances, their concentrations change during reactions, therefore they are always included in the Kc expression. If the reaction had been heterogeneous instead of homogeneous, homogeneous again because everything here was the same phase, all gases. If it had been heterogeneous, perhaps with solids or liquids present, we would have omitted any solid substances or any liquid substances from the expression. Solids and liquids, unlike gases, are not compressible, and so their concentrations are constant. If you think of a 2-liter sample of water versus a 1-liter sample of water, and ask, well, what's the difference in concentration? The answer is none. They're the same concentrations. You can show that water's concentration is basically 55.5 moles per liter. If you think of its density as being 1 gram per milliliter, 1,000 grams per liter, 55.5 moles per liter. That concentration is the same whether there's a lot of water or just a little bit of water. So water and other liquids or solids have constant concentrations, and so we do not include them in Kc expressions. Right? The value of the equilibrium constant, which is determined using concentrations or pressures at equilibrium, a key idea is that its value does not depend on the initial conditions in the reaction. It depends only on the temperature of the reaction, and as we'll see later, on the way you balance an equation. Let's illustrate that with a little animation. I'm going to click on this little icon here. If you want to type that URL into your own browser and look at the animation yourself, go for it. I'm going to look at the video here and play it for you. So we will open up a browser. I'm a little unsure how this will work.
Consider the chemical equilibrium between dinitrogen tetroxide, N2O4, a colorless gas, and nitrogen dioxide, NO2, a brown gas, at 25 degrees Celsius. Analysis of data for this equilibrium shows that although the ratio of the concentrations of NO2 to N2O4 gives scattered values, the ratio of the concentration of NO2 squared to the concentration of N2O4 gives a nearly constant value that averages 4.63 times 10 to the minus 3. K equals the concentration of NO2 squared divided by the concentration of N2O4, which equals 4.63 times 10 to the minus 3, where K is the equilibrium constant for the equilibrium at 25 degrees Celsius. Note that the exponent 2 for the NO2 concentration in this expression is the same as the stoichiometric coefficient. To convince yourself that the above equilibrium expression holds, no matter the starting concentrations, choose to start the reaction with pure NO2, pure N2O4, or a mixture of NO2 and N2O4.
All right, in that little introduction, you hopefully followed the Kc expression. They just called it K, but we would have called it Kc with concentrations. There was the concentration of NO2 in the numerator because that was the product of the equation as they wrote it, squared divided by the concentration of N2O4. They said that at a given temperature, the temperature that the reaction was being done at, its value, the Kc value, was, I think, 4.63 times 10 to the minus 3 or something like that. Well, we're going to do 3 quick little experiments here, and in each experiment we're going to change the initial settings, and we're going to see how that affects, if it does, the value of Kc. So let's start with pure NO2 in a container. So imagine a flask which we fill with NO2. NO2 is a brown gas, so that's going to be a brownish looking gas in the container, and initially we don't put anything else but NO2 in. If you look back at the balanced equation, the equation, I'm just going to write it here for you again, was I just lost my pen, N2O4 becomes 2 NO2s. So if we're going to put NO2 in the flask, then we're starting with the NO2 and the reaction has to go in the reverse direction. In the second experiment, we'll start with just N2O4. The reaction will have to go in the forward direction. In the third experiment, we'll start with both of the substances, and we will see when we look at the reaction the direction that it proceeds. So now let's jump in and start the reaction.
Starting with 0.200 molar NO2, the reaction proceeds toward equilibrium with NO2 molecules combining to form N2O4 molecules. At equilibrium, the concentration of NO2 is 0.0204 molar, and the concentration of N2O4 is 0.0898 molar. Calculating the equilibrium constant, K, we find K equals 4.63 times 10 to the minus 3. Recall that when chemical equilibrium has been reached, the reaction has not ceased. At equilibrium, the rate of the...
All right, I'm just going to interrupt the speaker there. Notice that in this situation, when we look at the graph, these numbers are not just made up. The N2O4 concentration, if you have a calculator, you can verify something for me. Its concentration started at 0.2 molarity, and it dropped to 0.0898. So if you take the difference between those, so 0.2 take away 0.0898, you can see that the N2O4 dropped by 0.110 molarity. Looking at our balanced equation, though, the NO2 should be increasing by twice that, right? Because it's a 2-to-1 ratio in the balanced equation. So if we multiply this by 2, we should get an answer pretty close to 0.0204. I just realized I'm missing something here. The N2O4, oh, you know what, I'm looking at the wrong numbers here. The NO2 started with 0.2, so let's redo that, 0.2, and the NO2 finished with 0.0204. I misread that. So 0.2 take away 0.0204, this 0.1796 is the change in the NO2 concentration. So now the N2O4, the ratio was 1 N2O4 for every 2 NO2s. Its change should be half as much. So if we divide this by 2, sure enough, we get the number they show there, 0.0898. If you take those two concentrations and plug them into your Kc expression, the Kc expression here will be the concentration of NO2 squared divided by the concentration of N2O4. You should verify that you get this answer for Kc. Pause the video here and try that just to be sure. So now let's go back and try the experiment again, but this time with pure N2O4 in the container. So the N2O4 is starting with a concentration of 0.670 molarity, and there's no NO2 initially in the container. And as it reacts, notice the flask is getting darker brown because now we started with a colorless gas, N2O4, and we're producing the brown gas, NO2. So now it's getting darker brown. We've reached equilibrium because the concentrations are stopped changing. If you again just make sure these numbers are not made up, the NO2O4 started at 0.67 and finished at 0.643. So if we find the difference between 0.67 minus 0.643, all right, it changed by 0.027. Then the NO2 had to change by twice as much because of the 2-to-1 ratio. So multiplied by 2, 0.054. So you can see that that number is not made up. If you take the NO2 concentration now and square it and divide by the N2O4 concentration, you get the same value essentially for Kc. So the value of Kc here did not change even though we radically changed the reaction. Now, one thing that might confuse you, so just to be clear, when you write a Kc or you specify a Kc, it always goes to a certain equation. It's not based on the direction the reaction is going. So because I wrote this reaction with the N2O4 on the left and the NO2 on the right, I'm going to calculate Kc the same way every time. NO2 concentration squared over N2O4 concentration. That will not depend on the actual direction of the reaction. So in the second reaction, N2O4 was producing NO2, but in the first experiment, we were actually going in the reverse direction. That doesn't really matter. Because I've written the reaction like I did here, the NO2 on the right-hand side becomes the numerator in my Kc expression. The N2O4 on the left-hand side becomes the denominator in the Kc expression. Let's do the third experiment. This time we're putting both substances in the flask. The flask starts off with a reddish-brown color, and it should react. So there we go. It starts off reacting, and at equilibrium, the color seems to me to be getting maybe a little bit less intense. The NO2 concentration is dropping, and the N2O4 is increasing. There's the two concentrations at equilibrium, and if you take those two concentrations, plug them into your Kc expression, you get essentially the same value. So in 3 different experiments with 3 totally different starting situations, we ended up with an equilibrium mixture that was different each time, right? The concentrations of N2O4 and NO2 in each of the 3 experiments was different at equilibrium. And yet, when we plugged those concentrations into the equilibrium expression, we got the same value for Kc. So the value for Kc does not depend on the initial concentrations in the experiment. It only depends on the temperature at which you're doing the experiment, and as we'll see, on the way that you balance an equation. All right, I think well, you know what, let's look at this. We didn't actually look at this animation in class, but let's try it. We've got a similar reaction, not quite exactly the same, but N2O5 is decomposing to make the brown NO2 and oxygen. So let's start. We've got these N2O5 initially at 0.02 molarity, and we have 0 of the 2 products. Let's start the reaction and see what happens. Okay, so the N2O5 is decreasing, the blue curve, while the orange and the pink curves are increasing. Those are the 2 products. You can tell here we've just reached equilibrium because the concentrations are all now constant, and you can see what their values are. If you want to try calculating the Kc value for this reaction, that would be a good little review. So let's write the Kc expression. I'm going to do it beside this. Kc will equal, these are all gases, so they're all going to be included in the Kc expression. Concentration of NO2 to the power of 4, its coefficient is a 4, times the oxygen concentration divided by the concentration of N2O5 to the power of 2. If you take the concentrations measured at equilibrium, which we have here, these concentrations are here at equilibrium, right? And plug them into the Kc expression, you should be able to evaluate Kc. So Kc here, the NO2, 0.0396 to the power of 4. And we multiply that by the oxygen concentration, so multiply by 0.0099, and divide that by the N2O5 squared, so 0.0001 squared. So for this experiment at this temperature, the Kc value is 2.43. 2.43. All right. If these are all gases, we could have also written the Kp expression. I'll just quickly do that here. The Kp expression is done using pressures. So it would have been the pressure of the NO to the power of 4 times the pressure of the oxygen divided by the pressure of the N2O5 squared. And we would have to know the temperature. We do here. Here's the temperature, 1700 Kelvin. We could use our ideal gas law, PV equals nRT, divide both sides by volume, and recognize that moles divided by volume is concentration. We could take our 3 concentrations right now and convert them to pressures in atmospheres. We'd use 0.0821 for the value of R. We'd use the 1700 Kelvin for temperature, and we'd use these molarities for concentration, and we would then know the pressures in atmospheres. We could then evaluate Kp if we wanted to as well. So there's just a quick overview, introduction of equilibrium, connecting it hopefully for you to kinetics and concentration time graphs, as well as the rate time graph that we saw earlier, remembering that the definition of equilibrium, the point in the reaction when the forward and the reverse rates become equal, and then at that point all of the concentrations remain constant.